Just an announcement to you. You may see me hobbling around a little bit, limping around. Somehow yesterday I twisted my knee and it's extremely sore. It's a little bit better today. It was really bad yesterday. But in case you see me hobbling, that's why. I don't even know what I did, but something. So. Now, we're going to talk about Newton's second law primarily today. It's a huge topic. So we're going to give you kind of a bunch of concepts. We're going to do some talking PDFs, in other words, on the document camera. I think two different examples on the document camera. And we're going to try to apply Newton's second law to skateboards. Raise your hand if you've got a skateboard here in class today. Let me see your hands high. 1, 2, 3. Okay, we got, good. We're going to need more than one skateboard, hopefully by the end of the class. And get your clickers out and have them ready. But before we get to any of that, I want to give you a couple announcements about this and that. Concerning the exam coming up, which I know is on everybody's mind. There's going to be a special S.l.review run by Maria. It's posted at the top of the homepage of web courses. Here's the data. It's going to be next Wednesday at 4. And I don't know if it's going to be 1 hour or 2 hours, but I'll try to add that information in. I'll know by lunchtime, actually, lunchtime today. It's going to be Classroom Building 1. So this is Classroom Building 2. Classroom Building 1 is just across the courtyard and in room 107, which I believe is a big lecture hall. And the objective for that is to help you prepare for Exam 1. Now, a lot of you are nervous about Exam 1, and yeah, I can understand that. It's your first exam with me, and so it's kind of hard to know. And even if you've had students in my class, or if you have friends that took my class, last year or something like that, still, if you haven't taken one of my exams, you might still be a little nervous. But going to SI is going to really help, especially the S.l.review. And as always, if you can't make it, just try to, if you can make 30 minutes, make 30 minutes, all right, if you can. If you can't, you can't. And I believe she has a Google Groups, and I think there's a Facebook group for SI in this class, but I don't. The SI leader, Maria, actually works for SARC, so she doesn't work for me. So I kind of know a few things about what she's doing, but I don't tell her what to do. She does all that stuff herself. But hopefully it'll help you crush Exam 1. And as always, I have Wednesday office hours. We had a good session yesterday in office hours. We had a couple students come in and we just worked on problems and stuff and concepts. And we're going to do it a little bit more today. All right. And I always love having students come in office hours. So we'll have those next Wednesday. By the way, Darian, did you decide?
Yes, I'm going to have them at 1 o'clock on Mondays in the atrium.
Okay. Till?
1 to 2.
Okay. In addition, Darian, why don't you stand up and say what you just said to me?
I'm going to be having office hours every Monday in the atrium of the Physical Sciences building from 1 to 2 o'clock. Usually there's only a couple of people who come, so it's a lot of one-on-one if you need specific help with questions. I usually am pretty helpful when it comes to test questions and everything.
That's an understatement. She's very helpful. But good, thanks, dear.
It's in the atrium of the Physical Sciences building, so it's where Dr. B's office hours are, that building, but it's right when you walk in. There's a bunch of tables.
Yeah, so there's a bunch of cafe tables. It's a big open area. They call it an atrium. And just go into go past the student health service, go past Sumter Hall and the counseling center, right and left, and go and right by the shuttle bus stop there outside Sumter and the counseling center. That's the physical sciences building. And just go in the main entrance and you'll see Darian on Monday at 1. And she definitely will be very helpful for you. If you can't make it to mine, it's going to help you if you can get to Darian's. Another thing that I want to mention to you, something that we have been working on, and I know a few students have messaged me in web courses about it. Their iClicker, and we're getting more and more people, and I'm still not convinced that it's working properly, but it does seem to be cooking. The thing about iClicker, you have to register it through web courses only. Now, in our web courses page, the navigation menu over to the left where it says iClicker, just click on that, and it's mandatory that you register through that, and I'm going to go through some of the ramifications of that. It's actually 10% of your semester grade. So technically, you can't get an A without iClicking pointage, at least well, actually, you can get an A if you ace everything. But if you don't ace everything, you're going to have to get at least a few points from clicking. So you've got to get this done. Now, if you go into the home page, I set up a little line on your grades page that's indicated. You might have seen this yesterday or today. The little blurb to announce that there's a new grade bit of information in there. And it looks like this. iClicker is registered. 1 equals yes, 0 equals no. And for this particular student, that student is marked down as a 0. So they're not registered. Now, you may say to yourself, well, Dr. B, I'm clicking in class. I get the Go Nitro. Yeah, that's very nice. That's known as anonymous polling. All right? And iClicker is set up to be used by people that are registered and by people that are unregistered. If you're unregistered, it's not very good. It looks something like this. See that? All right, see, look at this. Somebody's clicking with that. That's the serial number. That's all I get. Until you register 979F9E96, that clicker, whoever it is, I don't know who they are from Adam. All right? That's the way the data look like to me. And you see a bunch of other ones, it's in red. All right, so that's what anonymous polling looks like. So do not be deceived that just having a Go Nitro and a check mark and all that stuff means that you're getting points on your semester grade. You are not. Your grade is going to be toast if you do not register. So get registered in web courses only. All right? Now, I registered a few people during office hours. We kind of forced the system, but the system is working, and I'll just remind you again that there is a discussions thread for people, giving tips and stuff. Now, are there any additional questions? Yes, Claudita. The question was, is there anything you should be focusing on for the test? A variation of that question that I really hate is, Dr. B, are you going to give us a study guide? And that tends to be from newbie freshmen that just a few months ago were high schoolers. Okay, so that study guides and stuff like that, I don't do them. Your lecture notes are your study guides. All right? And you have adequate opportunities to develop and perfect your lecture notes. Lecture notes are the center of what you should be considering. And then on top of that, or secondary to that, are clicker questions and homework questions. And behind all of it is the textbook that's designed to, enrich everything that we talk about in class. In addition, there is a discussion area started by Ashley Seifert, and she asked, I am wanting to begin studying for the first midterm. What types of questions can we expect? Will we mostly be solving equations? Now, I asked the two TAs to contribute answers, and they have started to do that. All right. Here's a little bit of a screen grab of Caroline Pittman. She's usually in the second lecture. Darian, up front here in the first lecture, she's also contributed. So definitely, if you're nervous, you want to get some good advice, listen to Miss Darian, listen to what Miss Caroline says, and then try to follow their tips. And just know that I understand that you're going to, really be nervous about it. But if you keep in mind what I've just told you about lecture notes being the kind of like the nucleus of your prep, you should be good. And in fact, I noticed when I read Darian's contribution, she mentioned going over her lecture notes using the YouTube, so that's a good tip. Anyways, I offer that to you, Claudia, for asking the question, and for all, so that everybody can benefit from their wisdom. Okay, last time we were talking about Newton's first and second laws of motion, and we're starting to get down to the nitty-gritty. I mean, true, we're not driving cars off cliffs, but we're ready to handle the calculations of it. And I want to do some clicking questions with you, frequency AA. So if you're using your clicker for the first time today, hold down the power till the square flashes, and then type in AA. And you shall be ready. So let's do a couple questions about the first and second laws and stuff like that. Some multiple choice, and we're actually going to do a calculation question today too. So be ready to, well, just hold on to your hats. I'll just put it that way. First question. Look at these velocity graphs. Oh, I love it. The whole class has gone silent because you're all reading and thinking. Got you right where I want you. Which one indicates an object speeding up from rest? 20 seconds. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And that's roughly 1 minute. By the way, students, on the midterms, I budget roughly, traditionally, I was told by my department chairman, 10 years ago, budget 1 minute per multiple choice question on a midterm. And so we have about the equivalent of 50 multiple choice questions. And so for a 1 hour test. And we actually have 75 minutes, so we're looking good for time. Okay, we're a little bit over budget, or I should say a little bit under budget. In other words, you got more time, more than 1 minute per question on average, so hopefully it'll be good. All right, now let me see what you guys voted for. Oh, man, you guys, geniuses, because the correct answer is D. That is correct. Very good. But now, so that's nice. And you know what? That's the kind of question, if I were to write a question like this for the midterm, that would be a basic question. And when I say there's enough basic questions so that it's tough to flunk. That's kind of what I mean. All right. Now, I'm not saying that this question is going to be on the test, but performance-wise, yeah, you guys knocked that one down. Now let's try another question. This is a little bit trickier. Okay, so I've highlighted over here graph number 3, Roman numeral 3. And hey, you guys, when you are taking these in class, clicking in class, definitely, if you feel like talking to your neighbor, well, what do you think? Or if your neighbor asks you, are you sure that that's right? Just talk. It's fine to talk. And I see a bunch of you guys doing that. I want you to be encouraged to do that because it helps you to think. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 225 answers. And that was the first question. I gave you 55 seconds. This one I gave you 65 seconds. Average 1 minute. Here's the answer. The motion is of an object that is at constant velocity. Now let me see what you guys... Oh, man. You guys are geniuses on that one, too. Nice. All right. But we're not done. I'm trying to... I want to see if you guys can really get all this stuff. All right. Question 3. Multiple choice. The blue car... moves to the right at constant speed. What does it mean? Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys voted for over here. Oh. It looks like a lot of you voted for B. And you guys are geniuses. So you do, all right. Well, we're not done yet. And here, but I do want you to take some notes. So make a note for this question. And frequently the questions, I set them up to be the basis for a little bit of notes, a little bit of discussion. And that's what I have here in this case. I want you to go down below the little VW, the blue VW, drawing a dot to represent the center of mass of the car, instead of drawing the car itself. And just give it a little rightward arrow, kind of medium size. And then you could say to yourself, yeah, constant speed to the right. Another way of saying that is that v subscript I as a vector, maybe 10.5 meters per second. That's 20-something miles an hour. That's normal speed for a car. Kind of poking around the parking lot or something. And to the right, because for a velocity, which option B mentions, you have to specify the direction. And a force, as we talked about in office hours yesterday, a force can act on an object and only change the direction, not the speed. That's possible. And we'll be talking about that today and next Tuesday. All right, so specifying the speed and the direction, yep, and a force can change either one of those or both. All right. Now, we're still on the blue VW, but now I've got a real question for you, and I'm sorry, but we have to get down to business with this one. So on this one, I say to one, I say to all, read carefully. On homework, clicking questions, most of all on exams. Dare, I want you to include a statement about this question when to the results of this question when we get to it. I'm going to give another minute or so. And I want you to refer to it as the question, statement, or set of statements. See that phrase up there? Okay. "30 seconds. And this one, I'm giving you a little bit more time on this one because it's a little bit more deluxe. And on the exam, if you take, an extra 30 seconds, that's all right, because some of the questions will be pretty fast. So, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right? All right. Now, Darian, I want you to make a comment about this. There, my wonderful students, is a spread in the answers. Now, what that tells me is that there's a variety of opinions about what the correct answer is. But I don't have a variety of opinions. I know exactly which of these are correct. So let's look at them. All right. First of all, constant velocity is a possible description for something that has no forces acting on it. So put a check mark next to that. Oh, did I say put a check mark next to it? Yeah, why don't you write this down in your notes? It's a question that's a good kind of a little mini note, side note. Now, what's wrong with this one? Option 2, Roman numeral 2, is no good ski. Why is that one incorrect? How would you say? Give me an answer. Raise your hand if you want to verbalize an answer. Sarah. Perfect. If you have an unbalanced, is that what you were thinking? If you have an unbalanced force, it's going to accelerate, right? So if it's constant velocity, that means if you know it's constant velocity, that means it's not accelerating. Therefore, you don't have any unbalanced forces. Now, option 3 is kosher. You can have forces on them, but if they add up to 0, 100 units one way and 100 units the other way, no problem. Constant velocity. So that one is possible. That's like Newton's first law. And option 4 is also correct. All horizontal forces balance each other and all vertical forces balance each other. That's actually equivalent to number 3. It's just a little bit more detailed version of Roman numeral 3. So, for this particular question, and you know what, guys? I love putting questions like this on the midterm and on homework. So, just a word to the wise. There's your correct answer. And whoa, now let's look at the results over here. Most people went for option B. Whoa, that's a lot of incorrect answers. But now, hopefully, if I ask a question like this on the midterm, that'll be a little bit lower proportion of people getting. And actually, the majority of people. See, the thing about this is, the only wrong answer is Roman numeral 2. So for the options down here, B is impossible. B is no good. Let's see. E is actually no good as well. And we got a couple people over here. So let me look at that again. So 53% answered incorrectly because they included Roman numeral 2. And if I was writing, if this were a written exam and you circled your answer or something, I could not mark this one wrong because it actually is a good description. Same thing with Roman numeral 3. Same thing with Roman numeral 4. But the best answer is, of course, option D down here. So remember that when you're trying to think through my questions and crush my exam, which I want everybody in here to think in terms of putting a beat down on every single clicker question, every single homework, and especially every single exam. All right? All right. Now, I want to ask you some questions now, or work with you to talk about Newton's second law in 2 dimensions. And what we're going to do is go into the details of this ballistic arc. And actually, this is a Ferrari driving off a cliff arc. Question?
That last scenario, is there friction included in that?
Possibly. But no matter what the forces are, if you have constant velocity, whatever forces you have, they balance left and right, up and down, away from you or towards you. Okay? Whatever direction they are, the net force is 0. And that's the observation that you make is constant velocity. So if you observe that, you know that whatever the forces are, they balance out to 0. The net force is 0. You might not know what the force is. Matter of fact, you may think, well, I know 3 of the forces, and I know they can't balance those 3. So there must be a fourth force that's balancing the others, and that gives you a clue of what to investigate. So, all right.
So in this scenario, there's no extra energy required to keep the vehicle moving?
I didn't say that. And in fact, I'm about to talk about that very thing. So thank you for leading into this question. Now we're going to try to we're going to work on the actual shape of the arc after it drives off the cliff. But what I want to also reinforce, and what's your name again? Yo, you that were behind this girl. What's your name?
Jordan.
Jordan, this is going to be an example that answers the question that you were asking. Because we're going to do the arc after it goes over the cliff. But before we do that, I want to just think about, what's happening before it drives off. So let's go back 1 second in time. T equals negative 1.00 seconds before it drives off the edge. Okay, so this point right over here where the car is written down on the left. And let's just talk about that. Go ahead and put a dot down here towards the middle somewhere. Make sure you have a little bit of room to sketch. And let's just start making a list of the forces that we know are acting on this. And this is, Jordan, this is going to be realistic. So we're going to have a bunch of different forces. First one, always, weight force downward. So give that a good size arrow, a good size vector downward. And we're up on top of a cliff. We're up on a mesa or a plateau. And it's rigid. So even though there's some downward weight force on the cliff also pushes the car up with exactly the same size force. And we would call that the rigidity force. I'm using the symbol N here because traditionally that rigidity force is all, in fancier terms, is known as the normal force. Okay, so I'm using capital N here. And so, Jordan, here are two forces that are in action against each other and they balance. Okay? All right, and we know that they balance because there's no vertical acceleration upwards or downwards. Side note, the normal force, the rigidity force, exists because the molecules in the minerals that make up the stone in this cliff, or the rigidity of this tabletop up here, you know, that's steel and hydrocarbon plastic. Those molecules are like they form like a network. The surface is like a network of molecules, and they act like a really, really tight trampoline. And everybody knows that if you stand on a trampoline, it'll sink downward until the springs are pulling you up and enough to balance your downward weight. So if you get on a trampoline, it's going to go down like 3 inches. But if a little shrimpy first grader gets on a trampoline, it might just go down 1 inch. All right? So it depends on how big you are. And the rigidity force is similar to that. So it's similar to a trampoline force, except it's submicroscopic. It's all the molecules, supporting upwards. So whatever the weight force is, within reason, the trampoline, the intermolecular trampoline, will hold up. Okay, now, as you were asking, Jordan, in a real car, you've got to apply the gas. You got to hit the gas. So let's use a rightward force arrow, capital F, to symbolize the fact that you got to put the pedal to the metal, as the saying goes. You got to hit the gas. We'll call that the applied force, capital F. Now, contra to the applied force, as you know, is some frictional force. All right, that always opposes the motion. All right, so if you're trying to go across the surface, if you're sliding across the surface or rolling across the surface, you have a little bit of friction, and the traditional symbol for that is lowercase f. So draw a smaller arrow, but those two arrows, little f and big F, the applied force and the friction force, whatever you do, they should be the equal in size, as close as you can make it. All right? So that's the dynamical situation, or a sketch of the forces on this car, symbolized by the dot. The center of mass is symbolized by the dot. Those four forces. Now, if it was an even more realistic example, you might put in, if it's a windy day, you might put in some wind off to the side. In other words, going into the screen or coming, like a side wind. So if you're trying to drive down the turnpike to Miami through a storm, a lot of times you get buffeted, or if a semi goes past you, and even a smaller car as they go past you, you can feel it push you on the springs left and right. Okay, so you could, think of an even more realistic example with forces like that. So whatever you have, if it's constant velocity, you're going to have a balance of forces. And this is a fairly realistic example. Questions before we continue to the Ferrari over the edge of the cliff? Yes. Go ahead, in the back, yeah.
I don't understand why if the force if the friction and the applied force are the same, how would it be accelerated?
It's not. We're assuming here that it's at 10.5 meters per second. Okay, constant velocity. So what I'm saying is, at the instant that this thing drives off the edge of the cliff, we're no longer in a state of constant velocity. Okay, and what I'm saying is that before he gets to the edge of the cliff, in this example, let's say that he's on cruise control, so constant speed, constant direction, okay? And therefore, we know that whatever else is happening, all the forces balance. And this is a fairly realistic set of forces that we know are affecting this car, okay? So I should have said my assumption here is that he's on cruise control. And if that's the case, then yeah, the forces balance. Okay? Is that a satisfactory answer? Okay. Another question? Yes.
Where's gravity in this?
Brandon. Yeah, where's gravity? The weight force. W equals mg. Remember that? W equals mg. The weight force, that's gravity. Yep. Another question. Yes. They're not all equal, but they all balance. The left and rights balance. They're equal in size, but opposite in direction. The verticals balance, and they're bigger. The verticals in this diagram, in this example, I made them bigger. The weight force is usually bigger, a lot bigger than the friction. Okay, so the arrows vertical are bigger than the horizontal arrows, but whatever else we know, if it is in cruise control, then the left and rights are going to balance. The ups and downs are going to balance. I'm not saying that. What I'm saying is that there's different ways to get inertial motion. Either you're way out of space, far away from any galaxy, so there's no force, not even gravity, and you're just zipping along at 10.5 meters per second. That would be no forces. But here on Earth, you can... Good. This is our other TA, Mighty Caroline. She's usually here for the second hour. Are you here now?
Yeah, I can say I just gotta go get a table for tabling later, so I'm just
Okay,
gonna
good.
store it here if that's
Yeah,
okay.
good,
All
good.
right, I'll be right back.
No problema. So anyways, yeah, so that previous question, the sets of statements, 3 and 4 were equivalent, but item 1 was not. That one is like out in space between galaxies, just kind of nothing. But on Earth, yeah, you can still have net force 0, but the constituent forces, the forces that go into the net force, might not be 0, and that's what we have here. Yeah, number 1 is from the last question is, the hypothetical far out and lost in space. It's kind of a hypothetical. Anyways, let's look at this arc. Here we go. Now we're going to put together some concepts, and then we're going to go to the document camera and work out the concepts. And so this is from the time t equals 0.00 seconds. And so what I'm saying is, the moment that it drives off the cliff, I start my clock. T equals 0.00 seconds. Now, after t equals 0.00 seconds, what do I know? Well, first of all, I know that gravity is vertical, and Brandon, the weight force W is still in operation, but there's no normal force. Once you've driven off the cliff, there's no upward force to balance the weight force. And so now you've got an unbalanced force. Okay, we know what the acceleration is. And hey, you guys, we're going to use a negative 9.8 here. 9.8 negative meters per second, because now we are trying to work in 2 dimensions, and we want to be mindful of up and down, below the x-axis and above the x-axis. To the left of the y-axis, to the right of the y-axis, we want to be mindful of that as well. All right, so if we have something downward, we have to give it a minus sign. And if we do that consistently, we can handle it. Okay? Now, I'm going to put my x and y axis right up here at the edge of the cliff in a second. But before we do that, we have to talk about the horizontal component of the motion. There's no such thing as horizontal gravity. Gravity is just vertical. And so the initial horizontal component of the velocity doesn't change. Now, the vertical component of the velocity of the Ferrari going off the cliff does change. It starts at 0 because it's running on the level at the top of this cliff. And then as soon as it gets off the edge of the cliff, then it goes from 0 vertical velocity to downward. It acquires downward speed. But horizontally, you're just, So there's no horizontal acceleration. And so to express the horizontal coordinate, the x-coordinate, as a function of time, we're going to use distance rectangle technology. And for the vertical part, distance triangle technology. All right? So we're going to have a 1/2 gt squared in the y-coordinate, and we're just going to have a v times t in the x-coordinate. And we'll do that in a second. Before we go any further, though, let me make a note. Here's my x-axis, and here's my y-axis. So I'm just saying at the very edge of the cliff, that's the origin of my coordinates. So my initial conditions are going to be these. And let's just use this speed that we've been talking about already, 10.5 meters per second. So this guy's going off the cliff at 10.5 meters per second. And it's a flat cliff, so the vertical component of his velocity is 0. So in other words, his velocity arrows is sideways. It's parallel to the x-axis to start. Now, when he's down here below the cliff top and he's on his way down to his doom, he's going to have some downward meters per second. But up here in the initial position, nope. Just flat, horizontal meters per second. And we'll just say 10.5, just so we have a round number. All right? Now, the initial position we also need, and that's 0, 0. I've set up my coordinate system so that that'll be 0, 0 at the top of the cliff at the minute that he drives off, at the second that he drives off. Another implication of that, if you think about it, if this is the x-axis up here at the top of the cliff, and here's the y-axis, then wherever he impacts down here below the cliff, that's going to give me a y value that's negative because I'm below the x-axis. And that, my wonderful students, is why I insist and require that we use a negative 9.8 for the value of g, because we're going to have to keep track of everything. All right? Now, I'm going to go to the document camera, and I'm going to pause the podcast here. Pause the... Okay, and so once again, let me just remind you that what we just did, this is a right side up parabola, and what we just figured for the ballistic arc it has a minus sign, negative 0.044. That makes it an upside down parabola. So this is a diagram from page, I believe it's page 28 in the textbook. So if you want to make a note to study, and there's more in page 28 and thereabouts than what I've gone through. So between lecture and reading around in page 28, you should be good. Okay, more details about Newton's second law. Now, up here in the upper left, that's the definition of acceleration. Delta A is equal to delta V over delta T. Oh, by the way, I don't know if I mentioned this, but the first few questions on the midterm are going to be matching. And I'll give you a set of 3 or 4 formulas, and then some options, like the definition or the name of it or how you use it, and you match the formula to the concept. And so it's equivalent to a formula sheet, but it's actually something you don't have to memorize. You just have to recognize. So if you've done the normal amount of studying, you should be able to get those first 4 or 5 matching questions correct. And then you don't have to worry about memorizing formulas. Anyways, you may see this formula on here. Here's A equals F net over M, Newton's second law. And here's the other version of it, F equals MA. Now, I want to take this third equation, F equals MA, and where A is, I'm going to put in delta V over delta T. All right, so there it is. F is equal to M times delta V over delta T. And I really like this last version of Newton's second law because it helps you to think about what's happening. It's easy for you to think about time and speeds instead of accelerations. I mean, you know when you're going fast. You know when time is dragging. And so delta V is more common sensible to most people than acceleration, F equals ma. I mean, acceleration is nice, but it's built from measurements. Okay, so time, distance, mass. You got to measure the mass. M of F equals ma, you got to measure that. Acceleration you build from distance and time measurements. Okay, and acceleration is calculated from velocities, and velocities are calculated from distances and times. All right. And if you're thinking about something that comes to a stop, like if you jump off a box at the gym, if you're doing plyometric workouts, you jump from the top of the box onto the floor. You jump from the floor up on top of the box. So you're in motion and you come to a stop when you land on the box or when you land on the floor. Okay, so there's a stopping size or a stopping time involved with that. And I like to think of that, if you are working on some kind of a stopping time force or stopping force, it's instructive to look at the numerator and the denominator. Okay, so if you have more stopping time, delta T, the amount of time that your stopping force is applied from the box, the rigidity force of the box, or the rigidity force of the floor, if it's landing on the floor, that's what stops you. If you have more stopping time, the denominator is bigger, and therefore the force is smaller. Because remember, whenever you have a big denominator, your overall quotient is smaller. So 1/7 is a smaller fraction than 1/3. By the same token, if you have less stopping time, the denominator is smaller, and that means the quotient itself is bigger. So there's a larger stopping force. Now, why is that important for you? It's important for me because my knee is really sore this morning. And stopping force, big, stopping force, small, is an issue if you want to try to protect your bones. So this guy here, jumping onto the box and up or down onto the floor, if he doesn't bend his knees, it's going to really hurt. I mean, you instinctively you flex your knees when you land, right? And if you don't, if you suddenly land and you're not ready to flex your knees and you don't flex your knees, it's going to hurt it's going to hurt your knees, it's going to hurt your back, and you're going to lose your balance. So bending the knees helps you have a longer stopping time, and therefore it's an easier stopping force. Here's another example. Make a side note of this. Did you ever hear, like in second grade, a riddle that you tell your friends when you're in second or third grade? Okay, what's heavier, a ton of feathers or a ton of bricks? And everybody always says, oh, a ton of bricks. And of course the answer is no, they're the same weight because they're both a ton. Okay? Now, which is easier to stop in? A brick wall or a snowdrift? And for those of you from Florida, snow is this white crystalline stuff of frozen water. It's fluffy and nice especially when it comes down. I miss it. I've been in Florida 10 years now. It's over 10 years, I guess. So which is easier to stop in? Brick wall or a snowdrift? Snowdrift, because snowdrift, you come gradually to a stop. Brick wall, that's it. You come in like less than a tenth of a second, you come to a stop. So big stopping force. That's why in your side note mention brick wall, stopping force big, stopping time small, damage to my vehicle maximum. Snowdrift, stopping force small, stopping time big, damage to my vehicle 0. So that's another kind of colloquial or common everyday example. Well, it's everyday example if you live north of Florida. It was snow. I don't even know what could you stop in here in Florida that stops you slowly. And quicksand, no, that would kill you. Come on. That's no good. You get absorbed by the quicksand. Anyways, so if you think about it, if you look at a movie about snow, you'll see a snowdrift. All right, let's keep going with a few more questions about Newton's second law. Next question. Very basic. Liter bottle of water. $15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, did I say basic? Yeah, this one should be very basic, very easy to answer correctly. Let's see what you got here. Ooh, we got a mixture. All right, we got a mixture of answers. Now let's take a look at what we got. Here's the correct answer right up here. 1.000 kilogram meters per second squared. A mass, kilograms, times an acceleration, meters per second squared. This one here, that's all discombobulated. This one here, meters per second squared, that's an acceleration. So that's not a force. And this one here, 42, that's... That's the answer to everything except for this question. Now, notes, side note for this question. 1.000 kilogram meter per second squared is the official unit of force in the metric system. It's named the Newton, symbolized capital N. So a force of 1 Newton accelerates a 1 kilogram object at the rate of 1 meter per second squared. And we're going to be talking about newtons. But I want you to remember, anytime you see a newton in an equation, you can always write it as kilogram meter per second squared if you feel like it. And if you want to add this to your side note number 2, sometimes writing a newton in its fundamental units, kilogram meter per second squared, is handy if you want to do some cancellation. So, now, let me ask you about a 342 kilogram T-Rex. You ready? Hit the refresh button on your key, on your clicker. Hit the refresh, the blue refresh key with a little circular arrow, and let's start this question. Now, this is actually a replay from homework, so see how you guys do on this. And remember, I just want a whole number, so you don't have to do a decimal point on this one. 1 minute. Thirty seconds. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Pretty good. A couple of you, look at that. A few 3351s and 3351.6 rounded off incorrectly. Now, some more we're not done. We got a little bit more instruction here. A few more details about mass. Now, mass is the quantity that carries inertia. The more mass you have, the harder it is to change your dynamical state. The metric unit is a kilogram, and I actually talk about this in chapter 1. A gram is the mass of a cubic centimeter of H2O at just a little bit above freezing. So what you do to measure it, you balance the object in question with a countable number of cc's of water, basically. I mean, it's the theory anyways. So take a kilogram liter, a liter bottle of water, that's 1 kilogram. And and then put your basketball or whatever it is on the other side, and then take away cc's or add cc's of water until they balance. Okay, so now this one's not in balance yet. But once they do balance, the number of cc's is the number of grams. And if you have over 1,000 grams, you have 1 point something kilograms. And so in this diagram, it's 1,000 grams over here in the left side of the scale, and the basketball, as you should know, is less than that. So, so you would take away a few cc's of water by some method, and then eventually they'd balance, and that would tell you how many grams in the basketball. So let's keep moving. I want to talk about Newton's second law and the directionality. So I've got a little diagram here of a toy car, a Ferrari, and the two-dimensional layout is starboard and port, forward and aft. If you get a force at 45 degrees from your velocity, say you're moving forward, and you get something like this little ball over here impacting your toy car, you're going to get a little bit of speed and a little bit of direction change because the force is perpendicular to your motion and some of the force is in line with your motion. You have forward and starboard force on that. So whatever the direction of the net force, that's the direction of your acceleration. So another way to knocked out my recording. I want to ask you to bring your skateboards to class on Tuesday next week. Also, homework 4 will be activated tonight about supper time. Now you're dismissed, 11:50. Good class today.